Okay, this is a companion video to the pressure flow Bernoullis, and it's going to go through the problem that we did in class using the calculator. The problem essentially was a run of about 4,000 feet of pipe that dropped from an elevation of 3,800 down to 3,500, and it was a 6-inch smooth pipe, which of course meant that in Bernoulli's equation one had to use the curve, where in fact the friction factor was a function of the Reynolds number, which meant in fact that it varied no matter what the velocity of flow was. Of course, the other cases would be where you have something with a rough pipe, when in fact very often you can just pick the friction factor first and you'll be correct on your first iteration. So here's, we're going to go through, we're going to load the calculator. First look at the program here. If we go to program, to turn on your calculator, obviously. Here's all the programs. Remember, one of them was Bernoulli, the other one was flow graph. Bernoulli, when you go through it, you need to, I'm going to run this right now and quit it out. I'm going to execute that, run the program now, and you see the length here. It gives you a length, etc. Now, this is not showing the revision date on this calculator. So the programs that, I have to double check how I loaded this up through, but remember, we entered a length of about 4,000 feet. Enter that. A diameter of 0.5. The friction factor was around 0.0125 when we finally got done. And then the head was about 300 feet. Now, it comes up with these numbers here. And in fact, these numbers are generally correct. This program did not need to be revised, but I went ahead and revised it anyway. I'm going to take this little bit here and now go out and double check that I have the right revision date on this program. That was one program. If we then go ahead, I'm not sure clear works or second off or delete or clear. Now if I go to the program, the second program is flow graph, and that's essentially going to graph the energy grade line, which is going to begin at the free water surface and then decrease with a slope that is equal to the friction factor divided by the diameter times the velocity head. That's all this graph is doing. And in class, I kind of pointed out I wanted you to do a certain thing in terms of pre-stacking your y equals, and I gave you the wrong variables to put in there. And so let's just see what this calculator program says now. Enter flow graph. This one does have the revision date. And if you note here, it's a simple flow problem. You're going to populate L1 with station and L2 with elevation like we did in class. And this is actually is the y equals Sx plus E, where S is that slope factor, which is equal to the negative of the friction factor times the divided by the diameter of the pipe times the velocity head, and E is the starting energy or elevation of the energy grade line, usually the free water surface. And then you need to make sure that you set your window variables before continuing, and you need a Moody diagram to do this. So if you go through here, this is going to ask you the Moody from Moody's diagram, 0.0125. Enter that. Velocity was around 13.5, I think. I should have written it down. The diameter was 0.5. The elevation at the start was 3,800. And this actually is designed to mostly fill out a graph, but it also will give you the elevation energy at any one point. So let's say we're going to go 2,000 feet away. And this is where in class it kind of stumbled on us. We hit an enter here. And that sounds reasonable. If you think about it, the energy grade line is going to start at 3,800 and go to around 3,500 if this is a freely flowing system. That means halfway down it's lost about half of its energy. Now, this is assuming no minor losses, and minor losses are going to be equal to some multiple, some constant times the velocity head. Remember to chant the Bernoulli's equation. You chant the Bernoulli's equation, and that means what? It means you write y and you say the elevation and foot-pounds of elevation energy per pound of material. You write P over gamma and you say the foot-pounds of pressure energy per pound of material, and you write v squared over 2g, and you say the foot-pounds of velocity energy per pound of material plus h sub p, the head of the pump, or the foot-pounds of energy per pound of material added at the pump, equals not yada yada yada, plus the head loss, where the head loss is equal to the foot-pounds of energy per pound of material lost throughout the run of the pipe due to friction. And remember, the whole hook to this is that head loss is proportional to velocity head, not to velocity. And so that's where you end up with a number of factors very often in an equation, one of them being F over D times L, which essentially is the slope of the line times the length of the line, being one of the factors that you count for in terms of energy loss. The other one being, of course, any constant. You lose about half a velocity head at an entrance into a pipe. You lose a lot of velocity through almost a closed gate valve. You lose, a lot of energy or velocity, energy loss, which is proportional to velocity head. You lose a lot in any particular places. Those are called your coefficients. And so what you will see is the energy grade line will step down at any place you have an instantaneous loss in energy. Now, there's a lot of analogies to circuits, and I'll probably put a few of these related to here. The calculation of circuit flow. It turns out circuits also modeled their flows using water, and water people use circuits to model their flows. All right, so that was this calculator punch. I'm going to go ahead and show you what I said you need to do with this y. I'm going to turn this back on, hit y equals. I'm going to hit pause right here for 1 second. Okay, I hit pause, and what I did there is I kind of pre-populated L1 and L2 using just my list commands here. If you remember here, you can go to stat and then edit. And if you look at here, I've got L1 and L2. Of course, I made the mistake of populating first LU, but then I can just use my kind of my stow variable to transfer from LU to L1. So you've got basically your station elevation. You remember that format's incredibly important. And the other thing you need to do, if I hit second quit here, is you need to set your window variables correct. So I'm going to start my 0 for my X. And my maximum on the X was about 4,000 feet down the road, down the pipe. My scale, you can set that any number, more or less. My Y, I don't need to graph the whole thing, so I'm going to go ahead, maybe go from 3,000 up to 4,000. 4,000. And my Y scale maybe of 10. Okay, 10. And I have now set my window variables. I can say second quit. And here's in fact what the equation needs to be when you look at the code or you look at the program. It needs to be actually SX. Sorry, hit delete here. It needs to be alpha S X plus alpha E. And remember, in the program, E is the starting energy. S is the slope, which is equal to F over D times the velocity head. And so if you now go through, and we ran through that program here, we can say second quit. Now if we hit graph, we should see 2 graphs if they're set up correctly. We'll probably only see 1 graph the first time, and that will be the function. And there's that function. Now we have to go back to second stat plot and turn on our stat plot. That would be effectively your list data. We're going to hit that. Turn it on, and depending on whatever format we like, we go down to here and we change the type there so it is crossing the it's actually graphing the data. Hit enter here. List 1 is my X, list 2 is my Y. I've got whatever mark I want to put on there. All right, second quit. Again, if I hit graph here, that's what the energy grade line looks like. Now, so here you have essentially the energy grade line, and here you have the ground grade line. What you have then, the difference between this and this is actually P over gamma plus the velocity head Realistically, you need one other line typically, and it's the energy grade line, and it's one below. We'll play around with these and use change the velocity here in the next video, but that's how you go about doing the program, and the program should be updated with an 1102 revision date. Thanks for listening.